Okay, so so yesterday we were talking about solving the NIM game, right? And so did anyone attempt some of the loose ends that were left? Okay, no, of course not, right? Okay. So what is the idea? So the NIM game, the way I defined was that if you have any heap, right, the heap with n elements can be written as a choice right. What does this mean? This means that I have the option of taking away all the n matches and go to a sub game which has no heap at all, or I remove n minus 1 sticks, or blah blah blah, right? So this is the idea. So in general I can talk about sum of games, right? That is, if I have a game G and a game H, so G, let's say, has options G1, G2 plus GK, and H has options H1, HL, then G plus H is given by, what does it have? What are the options? You can move in any one of these games or make a move in this game, right? So G1 plus H, or you can make a move in one of these games, G plus star H1, right? And then I said that I can define a notion of equivalence on these games. I can say that G is equivalent to H if and only if for every game J, G plus J is losing, if and only if H plus J is losing, right? This is the definition I gave. What's the notion of a game being losing? Look at the game star 0, that is losing, right, for sure. Now, if a game has a sum, one of which is losing, then the entire game is winning. Why is that? Because I have an option to move there, which will be losing for you. Yes. Oh, I have not. So that's winning for me. If I have a sum, all of which are winning, then it's losing for me. Right? This is an inductive definition, and we saw this yesterday. So you know when a game is losing, and this is the definition we have got. And what I was talking about was the fact that under this equivalence you get a very nice algebraic structure. Right? In fact, as I said, this acts as a 0, and on these class of games that is defined this way, you have let me say G plus is an abelian group. As it's 0. Yeah. And then I said there is an extremely interesting lemma which is at the heart of this whole analysis. What is that? This is what I said is worth proving. What is the lemma? Any losing game for any game G G is losing is extremely important, because this is that all losing games are equivalent. Right? That's what it says. So, and as I said, once you have this, whole lot of things can be proved immediately. For instance, you can you see one corollary which corollary if Z is losing, then you can always add a losing game without disturbing the winning or losing condition of the game. That's what it says. Of course, this is something we want, and that also you get. And okay. Right. Why is this true? For any game. You have to show, no? For any j, g plus j is losing if and only if g plus j plus 0 is losing, right? Okay, I'll leave it. I'm not going to do all this. So, but these are all straightforward statements, and this is extremely important, and this actually gives you the structural way of going about solving the problem that we're talking about, right? For two heaps, we already showed something yesterday. What was that? The proposition was that Mn is, I should write star, I should really use this notation since I have it. The two heap case. Right. So I know that in the two heap case, we directly analyzed and said that this is winning if and only if M and N are not equivalent. Because if it is equivalent, if M and N are equal, what can you do? You can do copycat, right? Simply copycat. And right. So now, since I know there is a whole lot of losing games, I can keep adding them and right. So, and I know that adding a losing game doesn't change the behavior. That's why I said larger heap lengths, right? Something with 5 heaps. Trying to directly analyze anything is horrible, but you can write it as a sum of 3 heaps and 2 heaps. Here, 2 heaps you know what to do, and then analyze the other one. And the 3 heap case, how will you analyze again? Bring it down to the 2 heap case and 1 heap case analyze. So this reduction is extremely important. This kind of reductions is what you want to do. And for the general one, as I said, this lemma proves extremely useful, because now I can use this to prove a lot of another corollary. Right? For all GH, what else to G plus, no, I don't want this. No, let me get to that later. So what about a proof of this? Anyone? How would one go about proving something like this? Stunned silence, come on. Tell me how. We need to do some formal proofs, right? We're just doing some. Yeah, by induction. What else? Because G is given to you by induction. These games are given to you with an inductive structure, right? So prove it by induction, right? So what is the induction hypothesis? So prove maybe here. We have enough space. Prove induction. Yeah. What is the induction hypothesis? There are 2 things hanging around, no? What do you need to prove? Okay, to prove for every j, g plus j is losing, this is what we need to prove, right? We need to do this if and only if. So let me prove this by induction. Yeah, I'll do the converse later, right? So we need to prove this later. For every j is losing of course for all g is there. Okay. Now this is what I'm going to prove by induction. Okay, so what is the induction hypothesis? Yeah. Remember that in your premise there are two games sitting here. So what are you doing induction on? Want to do on both, huh? Right? When you have this thing. So there are two induction hypotheses. For every j double prime simpler than j. What do I mean by simpler than j? What is the notion of g being simpler than g prime? G is a subgame of g prime, right? Subgame is what we had there. It's, in fact, it's one of the options. It's in a sum, right? If g plus j double prime is losing, then I have another induction hypothesis. For every g prime simpler than g, if g, let me use double prime. I want to reserve single prime for something else. Is losing, then j is losing. Note that these two are different statements, and therefore we should be careful about using these, right? Now I want to show that g plus j is losing implies j is losing. Suppose g plus j is losing. So this is something on stack. We'll continue here. Suppose g plus j is losing. What does that mean? What is the meaning of the statement g plus j is losing? For every option that I am the player, right, in g plus j. For every option that I can exercise, taking me to a subgame, that's going to be winning for the opponent, right? That's the only case where it can be. So that means, let me write, for every option, for every j prime subgame of j that I move to, right, g plus j prime is winning, right? Winning for the opponent, of course, because it's the opponent who is going to move. Winning for opponent, right? What does it mean to say that g plus j prime is winning for the opponent? When is a game winning for a player? There is a way of moving to a subgame which is losing for the opponent's opponent, which is me, right? That means there exists a subgame j double prime of j prime such that g plus j double prime is losing for me, right? But now my induction hypothesis tells me, right, in this case that j double prime is losing. Now what have we got here? In j, the game j, every subgame j prime is such that there is an exercise, there is an option j double prime which is losing. Therefore, j is losing. Is this clear? The induction hypothesis tells me that this j double prime must be a losing game. If j double prime is losing, what do I know? I'm starting with j. No matter what option I pick j double prime, j prime, the opponent has an answer j prime. Therefore, I have no hope of winning in j. Yeah? So this is use of one induction hypothesis. In the other case, let's So now this is the case where I am considering moving in the right hand side. I could also be making a move on the left hand side game. Remember, G plus, the plus allows you to move in this game or in the other game. So now I have to consider. So G plus J is losing means, so maybe I should call this A and B. B. G plus J is losing also means for every G prime subgame of G that I move to, G prime plus J is winning for the opponent. Same thing, right? It must be that both of these conditions must hold. G plus J is losing means A and B hold. Right? Some game is losing if and only if all the options that I am considering are. Even if one option is winning, I am winning, right? Because I picked that. Not stupid, right? So for every G prime subgame of G that I move to, G prime plus J is winning for the opponent. Therefore, there exists G double prime subgame of G prime that's losing. Yeah. Now, by induction hypothesis, yeah. So here what I am showing is G double prime plus J losing. G prime, G double prime plus J is losing for me, and therefore by induction hypothesis J is losing as a coin. Okay. So in both cases I have shown that if G plus J is losing, then J is losing. Is it, I am just going through the details. The idea is very clear, but it's better to write the steps and get it. There is another direction that's still to be done. Take this off. In fact, easier to do. What is this? This is the suppose J is losing. Right? I want to show that G plus J must be losing, right? Yeah?
G plus J prime is winning for the opponent.
Yeah, here, yeah? Yeah, okay.
Why is it implied as a subgame J double prime? Why can't it imply as a subgame G prime, such that G prime plus J prime is losing for me?
Oh yeah, so you have to consider two cases, A1 and A2, and again you can apply the induction hypothesis.
Okay, so that one.
Yeah? Yeah? This is true for every subgame, yeah? Is it clear? Again, even if you go down, there is a second induction hypothesis available. Identical argument can be used. You are right. Wait. In fact, sorry.
The second case he was talking about, the second case was taken care in part B, right?
Yeah, but formally, this only implies that in this there is some subgame that he can make a move to. That subgame could be here or it could be here. Right? Point taken. Yeah. Of course, this also means that B1 also has a B2. Right. Here also, G prime plus J is winning for the opponent means that either you could make a move here or you could make a move here. But again, you will get the application of induction hypothesis. But there is a smarter way of combining the two into one induction hypothesis so that you can avoid all this. But I'm not going to do that now. Let me just take this simple way out. let's get to the other direction. So is it okay? Will you let me go to the other direction? Yeah? No problem? Fine. So what is the other direction? I have to show that if J is losing, then G plus J must be losing. So consider, suppose J is losing, but G plus J is winning. It's winning means what? There is some subgame that I can go to, right? That is going to be losing for the opponent. So let me write that. There exists G prime plus J or G plus J prime losing for the opponent, right? I mean, I have to write G prime plus J where G prime is a subgame of G, G plus J prime where J prime is a subgame of J, etc. But I hope you pardon me for this, right? What do I know now? We have already proved this direction of the game by induction. Therefore, I can use it. From this, I'll get J is losing. And what about here? In this, I immediately get. Wait. One second. Wait. Let me just get this clear. Suppose J is losing. I want to show that G plus J is winning. Yeah, okay, let me handle this case first. This means that J prime is losing. This must be the case because I am applying the other side. If G plus J prime is losing, then of course J prime is losing. But if J prime is losing, this implies that J was winning, which is a contradiction, right? Because J is losing for the opponent, therefore winning for me. That contradicts our assumption that J was losing. What about here? This is interesting. Let me just see. Yeah, G prime plus J is losing. So yeah, G prime must be losing according to the by this direction. G prime is losing. Now, in addition, now what must be the case? Yeah, J should be winning, right? That's the only way you could have G prime plus J. This is losing for me, right? This is losing for opponent. Yeah, this is losing for the opponent. Wait, 1 second. Let me just get it, write it properly. G prime plus J is losing for opponent means G prime is losing for opponent. Yeah. Okay. Then J is losing for the opponent as well, right? That is the only reason G prime plus J was, which means J is winning for me, which is a contradiction. So this, remember that when we talk about a game which is losing, it only means that losing for the player who moves, right? So this is the, okay, let's see. So what does it mean for that G prime plus J is losing for the opponent? Now I'm saying we have already shown that G prime is losing for the opponent, right? Then it must be the case that J is also losing for the opponent, right? And if J is losing for the opponent, J could be losing for me. J must be winning for me, right? As moving to this subgame, right? Actually, I don't need to take this case at all. If we have already given that J is losing, we only have to consider only the subgames of J prime. That's all. In fact, I don't even need to do this. So let's see that you don't need to do this at all. Let's start from here. Suppose G plus J is winning, right? How could you be winning? Yeah. Suppose we move to G, what happens? You go to a subgame G prime plus J, right? Now this G prime plus J is losing for the opponent, right? And now we have seen that, what is it that we have seen? Right. I think I can write it in both ways. Which was I trying to do? Yeah, so that's exactly it. So I am in G plus J. So one branch I move to G prime plus J, and another branch I move to G plus J prime. If this is losing for opponent, I go. If this is losing for the opponent, right, I have to show that right. Now, yeah, this is what I have said. So J is losing for the opponent. Therefore, in the original game that I was talking about, something is wrong with what I'm saying. Let me just check. Suppose G is losing. How can G plus J be winning? That means G was winning. Just 1 second. No. I use the fact that in this case, therefore G prime is losing for opponent. That's it. Okay. Now G prime is losing for opponent. In this case, now yes. Yeah.
So we, as you said earlier, we don't need to consider this case, the case at the left, because J is losing as per our assumption, and
Yeah.
G is losing game anyway. So G dash is also losing game.
Why is not clear? Not clear, no? Not clear. Let me just see. G prime is losing for opponent.
G prime is losing game.
Sorry?
G prime is losing game, right?
1 second. Yeah? I have to get a contradiction here. Yeah. G plus J. So I make a move to a subgame of mine, which is G prime. Then now this I know is losing. So that means G prime is losing and J is losing. Now, how is that possible? For every J. Yeah. No. So this is silly. I'm sorry. Huh? I'm sorry. This whole thing I'm trying to prove only for a losing game, right? If G is losing, I am trying to show that G plus J is equivalent to G, right? G plus J is equivalent to J. Right? So I am only trying to prove for every losing game G for every J, I am very sorry, yeah, G plus J is losing if and only if J is losing. This is the statement being proved. Yeah, the statement is being proved for any game G. We are trying to show G is losing if and only if G is equivalent to star 0. So what we are trying to show is, see, of course one way is clear. If G is equivalent to star 0, then G is losing. You just have to prove in the other direction, right? So in this direction, for every losing game, we are trying to show this equivalence. This equivalence by definition means I have to say for every J, G plus J is equivalent to J, right? So that means for every losing game, I have to prove this, right? Now, so this is not for all G, so it's my mistake. For every losing G, this is true. Okay. Now, as it happens, as you can see, you don't really need that. That's why it can be combined. So now, of course, this is clear. Right. For every losing G, if J is losing, suppose now, take a losing G, let G be a losing G. And J is losing, but G plus J is winning, it can only be possible by going down this branch, and there I can apply the other. I'm very sorry about that. Good. See, I was telling you that we must do formal proofs because otherwise you make mistakes. So, okay. And this, of course, now makes a huge difference, as I said. Now you can start adding things all over the place and do these things. So another one that is of interest is, okay, so this is the one that I wanted to, right? So this is in fact the theorem. Theorem, also called the copycat principle. For any game G, I must say for any game, when I am talking about G in this class that is defined this way, it can be generalized to any bipartisan games of perfect information, 2 players, 0 sum, etc., but I am not doing that. And I am talking about any nim game G, right? G plus G, this is extremely sweet now. Do you see why? This is a corollary from the lemma that we have got. Any attempt on why that might be the case? Suppose G is losing, then what do you know? Of course, you know, from that you can get. Yeah? If G is not losing, then what happens? Look at the game G plus G. What are the possibilities? If G plus G is winning, that means what? I can move to a subgame G plus G prime, which is losing. Right? Yeah? Okay. Now, I called it copycat principle, so you should also. G prime plus G prime? Wait, there is a move, okay. Okay. G prime plus G prime, that's winning, okay. But what do you know? I can do induction, right? G prime plus G prime by induction, I can set it up, this must be equivalent to 0, right? Then how is it winning? Anyway, you work it out. Sorry, I couldn't hear what. I really can't hear you. You have to shout. You're too far away. So basically, I'm also saying that G plus G must be a losing game, right? The moment I'm putting it as equivalent to 0, that's what it means. Yeah? And this is why it's called a copycat principle, just doing that. So this basically also means that in such games, G is equal to minus G in this sense, right? This is the inverse. I said it forms an abelian group, and what is the inverse? The inverse is itself. These are self-dual in some sense. Of course, if you look at the book Winning Ways, this whole business starts getting really interesting when you move to partisan games, when they have different moves. And there, the really beautiful theorem, which is much harder to prove, shows that if you just take the game G and look at its dual, what is the dual game? I think I mentioned it. The dual game is the identical thing with the same set of positions, but the roles are switched. Whoever is player 1 here plays as player 2 there, whoever. Now, for those who know logic, that's in fact the inspiration for the so-called game logic. So, that the theorem in Winning Ways, which says that the duals acts as inverses in this game algebra. So you can actually formally study these algebras and prove properties. But for the NIM games, this is an extremely interesting one. Now, in fact, you can prove one more corollary. Okay, since we have got this, we can also do this one. Another corollary which helps. G is, okay, so what is it that I have got? Suppose G is equivalent to H, right? Now, yeah, G is equivalent to H if and only if G plus H is equivalent to 0. Like the star business, but I have to do this now. Yeah. Is this, you can prove something like this. Do you see why? Suppose, in general, I can write G as G plus H plus H. Right? Because H plus H is 0. Right. Now, if G plus H is 0, this implies that G is equal to H, right, in one direction. Similarly, you can do the manipulation in the other to check. So what is this saying? This is saying something extremely interesting. It says that, so it's equivalent to a losing game. So you can actually prove this corollary. If G and H are games such that for every option G prime in G, there is an equivalent option H prime in H, and vice versa. Then G is equivalent to H. Now, this is important to prove this because this is what you would have thought was intuitively the notion of equivalence that you should go for, right? What was the definition I gave for equivalence? G is equivalent to H if and only if addition of any losing game to 1 leaves the other one the same, right? G plus H is losing if and only if. That's a little counterintuitive when you think about it, because what it does is to equate all losing games. That's what we have seen. This is what you would have expected. Now, this is something that you can prove, but it's actually true only in one direction. This is the important reason why. This is a finer notion, and the implication for NIM is extremely important. What is the implication for NIM? So, the point is that losing games are all equivalent, but winning games need not be equivalent. Two winning games resulting in a win can have completely different sets of moves, different strategies, strategy spaces can be different, and that's really what this equivalence is about. So so now in fact one can prove as an exercise in fact this is the case for all Mn star M is equivalent to star N implies M is equal to N. That is, if I take two distinct nim heaps, right, they are inequivalent. And so this is the point I was making about. Okay, so I don't want to go on with this. The idea was to really motivate you to look at combinatorial games seriously, and I already gave some references yesterday. Did anyone look at Eric Demain's page? You should. There are really lovely challenges there. Okay, so enough of this class of games. Any questions about these NIM games or the game algebras or anything of this kind? Okay, fine. There was something else I mentioned yesterday. I want to tie up all this before I move to equilibrium. Take off these things. Oh yes, I mentioned this Ulam game yesterday, and the claim that there exists a game that is not determined. I think I should do a proof of this to show you what it means. What is this determinacy business? That, as I said, we are not going to do too much of this later on, but I hope again this will be a pointer for somebody interested to take up. So what is the Ulam game? So there are two players, 1 and 2. Player 1 picks a natural number x0. Player 2 responds with x1, x2, x3, and so on. Right? And for convenience, I assumed that x0 is less than x1, less than x2, less than x3, and so on. Right? And what you are given is a subset. What is this? A set of infinite sequences of natural numbers. So this is given. Now the sequence rho belongs to A implies 1 wins. Rho does not belong to A means 2 wins. Right? The Gale-Stewart version of the Ulam. It's okay. No, really, Ulam was really interested in precisely this sort of thing. Except the way he said it was, coming from 1930s, it was in a different language. That's all. Yeah, he's absolutely right. I mentioned this paper by Gale-Stewart, 1953. So everything I'm talking about comes from Gale-Stewart. So it's really Gale-Stewart version of the Ulam game. But I know that Ulam had this in mind. So okay, so now what's the strategy? Strategy for player 1. Sigma is a map from n to the, the way I've set it up, it's 2n, should I said x1, no? It's okay. Anything of odd length. N star. So let me just write it as n star. Right. To n. Right. And for player 2 is also, except that here you are talking about the initial string as well as strings of odd length. This is strings of even length. So please forgive me for not writing that. Now, when do you say the game is determined? So we have already seen. What does it mean to say sigma is a winning strategy for player 1? Means for all tau of player 2, sigma tau belongs to A. Right. This is the idea of winning strategy. A is determined if either of the two players has a winning strategy. Now we want to show that there exists a game that is not determined. Right? I want to set up a game. What does it mean to say? I have to define a set of sequences and argue that over this set of sequences, neither of the players has a winning strategy. Right? And the proof uses the copycat principle. That's why I thought we should see. So this is like, something that comes in lots of places in game theory. So like, how do you do that? So I'll set up a set U, okay, which will have the following properties. Okay, so it has to be a subset of n to the omega, right? Yeah. So let me first, I'll define a set of subsets of n which has the following properties. One is that it's closed under intersection. It's closed under subsets it doesn't have the empty set. And for so what is this set? The set of all n minus x such that x is finite belongs to U. This is the set of all cofinite subsets. And lastly, for every A belonging subset of n, either A belongs to U or okay. Consider a set like this. What is the set of families of? This is a family, right? Set of subsets of n. What are the properties it has? It's closed under intersection, closed under supersets, doesn't have the empty set. Actually, these two together say that it's a filter. This is just terminology. Right? This says, the third one says that it's a proper filter. Addition of this says that it's what is so-called Fréchet filter. These are like, famous objects, so I'm just giving it names. But don't worry about it, it's just a set. Right? And lastly, this one says it's a free ultrafilter. These are all nice things to know, so I'm just mentioning. But for us, we don't need all this. That such a set exists is something, constructing such a set. Because you're starting with this set, right? This must be there. You are starting with this set. Start with this set and simply close under intersections and upward, you will get this, right? Now, and you have to make sure that every set or its complement gets in. That requires a bit of work. This requires so-called axiom of choice. But this is equivalent to the well ordering principle, Zorn's lemma, all these things. If you know a little bit of basics about infinite sets, you can sit and do it. There is a construction, there's a nice construction that you can do, but I don't want to spend my time showing you that such a set exists. Let's just take it as, but anyone who knows some basic set theory and has done some, first bit of analysis should take it up and do it, okay. For those people, it's not a non-exercise. You must show that such a set exists. So, let U be such a set. Now, I am going to define my set AU, as follows. Consider any sequence, right? What is this sequence? I am interested in plays of this kind, right? A play of the game is going to give me a sequence of natural numbers x0, x1, x2, x3, etc. Right? So now consider the number line looking like this: 0, x0, x1, x2, x3, dot, dot, dot. Right? What I will do is to color these intervals. So let me color this green, and up till this point, and excluding that point, starting this, let me color red. So this will be colored green, red, all this, right? Yeah? So now, so consider any sequence rho like that. Rho belongs to AU if and only if the green belongs to U. If I take the union of all these green intervals, that's a subset of natural numbers, right? If it is there in the set U, then that means this is winning for player 1. That's why it's green, right? And you can see that red is a complement of the green, right? Yeah. So if green is not in U, I know that red will be in U by the last principle. So player 1 wins if green belongs to U, player 2 wins, you see that, right? When does 2 win? 2 wins if and only if rho does not belong to AU. That means if and only if green does not belong to U, if and only if red belongs to U by condition 5. Yeah? So this is the way the game is set up. Take any sequence, that sequence gives you a green subset and a red subset. If a green subset is there in the original set U, player 1 wins. If the red subset was there, then player 2 wins. Right. Now I claim that the game is not determined. How do we do that? Suppose the game is determined. Suppose AU is determined. We'll show a contradiction. Without loss of generality, one of the players has a winning strategy. So let me say without loss of generality, player 1 has a winning strategy. Say sigma. What will player 2 do? I'm going to give a way for player 2 to do something. Player 2 acts as follows. So player 1 will pick x0. So player 1 is playing according to sigma and picks x0. Right? Player 2 responds with some arbitrary x1. Okay? Now, at this point I have to ask this question. Do you know how to win how to at least not lose against a grandmaster in chess? How do you make sure that you don't lose a game against Vishwanathan Anand, for instance? Because that's what player 2 has to do now. Okay, player 1 is Vishwanathan Anand. You see, so okay. So this is why I am celebrating the copycat principle. So what I do is simultaneously I play a game against Kasparov. What will I do? concurrently I play two games where, let's say I am playing black against Anand, I play white against. So then what do? I let Vishwanath and Anand make the first move, right? Okay, then what should I do? I go to the game against Kasparov, make that move. Kasparov will respond, no? I'll take that response and give it to Anand. It's actually Kasparov and Anand playing against each other through me. But hopefully, let's see that, both are dadas, right? So it is going to result in a draw. So I'll make sure that I don't lose. And I go around telling people that, look, Anand couldn't beat me and so on, right? Huh? Neither could Kasparov. This is very important. And on a good day, that's the most likely. So this is exactly what our friend is going to do now. So player 2 starts off a concurrent game against player 1. I shouldn't say concurrent game because unfortunately computer scientists have hijacked it to a very different meaning. But anyway, so let me call this game G0 and a game G1. Now in G1, player 1 is going to play exactly the same winning strategy sigma, which means what? What is the first number that player 1 will pick? X0, right? Because if you play according to a strategy, that is the number that you will get. Right. I must respond here. What is the response I'll give? I'll watch here. Player 1 will respond with an X2 and I respond with X2 here. Right? Now for X2, player 1 is going to give an X3, which I'll copy here. I'll get an X4, which I do here. So I quietly keep doing this. So how does the mapping go? And I hope you will have the patience to write X2n and X2n plus 1 and 2n plus 2 and so on and so on. Right. So here is a sequence row, and here is a sequence row 0, row 1. What do we know about these two sequences? What do we know about the sequences? They are both winning for player 1. Why? Because player 1 is playing a winning strategy. By definition of winning strategy, it means no matter what response is given by the other guy, it's winning for player 1. So that means row 0 defines a green subset. Row 1 also defines a green subset. Now look at the intervals that are there. This one gives the interval 0, X0, I have to do all this, union X2, X2, X4, union X2, 0, X0, and X1, X2. X3, X4 and so on. So this is one. Here what is it that I get? 0, X0, union, X2, X3, union, this is this half open nonsense, X4, X5 and so on. Right? Now I know that this thing was closed under intersections, right? Let me call this set G1, no, I can't call it G1, let me call it X1, X2. So X1 is in U, X2 is in U, therefore X1 intersection X2 is in U. Yeah? What is the intersection? That means that the finite interval 0, X0 belongs to U. Yeah? But that's a problem, because what we started off with was the set of cofinite subsets. So therefore n minus 0, X0 belongs to U, because this is cofinite subset. Therefore the intersection of these two, which is the empty set, belongs to U, which is a contradiction. Right? Basically, a set like this cannot have a finite set. Right? If there is a finite set, you have a problem. Because if a finite set will be there, cofinite its complement will be there, by intersection, empty set will be there. So no finite set belongs to is in U. And that is a contradiction here, right here I should write. So this doesn't require deep stuff except some bit of jazz about how that set is constructed, and as I said, that's why I'm saying, and those are well-founded sets. In general, well-founded sets need not be inside the Borel hierarchy. So anyway, this is those who care about analysis, topology and such things. Fine. Enough of this. Again, if you are interested, please tell me, I'll suggest some more material, some very nice results along this direction. So in particular, infinite games, I am not and I think I mentioned the motivation yesterday. In the verification of reactive systems, there is a, in the algorithmic analysis, this kind of infinite games proves extremely interesting, and I mentioned that there are also nice open problems. So that's about the second landscape. In the landscape of game theory, I mentioned there are three branches of very interesting study. One is the combinatorial games. Infinite games. Now, what is extremely interesting to me is that classically infinite games have been studied by topologists and set theorists with the kind of flavor of arguments that I have given. But there is some subclass of infinite games that come here which have nice correspondence with it. Computer scientists are coming up with interesting analysis that cuts across these two and cuts across to the third one also, namely the what I said, economic games. Or really the right term for this is equilibrium theory. So what is this, and let's look at that. That's what we'll spend the rest of the time on. So yesterday or whenever we have been talking about extensive form games, which are really finite trees, right? Some finite trees. At the leaf nodes, you had a winning condition which said this leaf node is winning for player 1, this is for player 2, this is for player 2, this is for 1, etc., etc., right? Instead of simply saying that it's a win-lose game, you could also have a more general definition. So rather than going from the win-lose, you can go for general outcomes. What does that mean? The play, you go through the play, it results in some condition. That win-lose only means that that condition is favorable for you and it is against for you. But the more general idea is that when we finish the game, maybe we get some money, right? So money is, since this comes from economists, all outcomes are translated as getting money. Or if you get punished, it's like getting negative money. You pay a fine, right? So this is the idea of having a utility. So instead I could have numbers sitting here saying this is 3, 4, 15, 0, 8, 16. What does this mean? If the game ever gets to this leaf node, player 1 gets 3 rupees, player 2 gets 4 rupees. In this case, player 1 gets 15 rupees and player 2 gets nothing, and so on. Right? So this is, you can think of it as a utility function. What is it? What is the utility function? From the leaf nodes of the tree to the set of real numbers. Again, for whatever little bit we are going to discuss, don't worry, we don't have to think about real numbers at all. You can think of rational numbers, will do in general. Not for the general equilibrium theory, but for the purposes that we are going to work with. Integers is what I'll use. Now, So if this is so, so what do the players play for, right? Earlier, a game you play, right? Now what do you play for? Maximize your expected utility. Okay. So now there is one kind of thing that I didn't talk about at all. The kind of nodes that we had were always things of this form. Right. That is, what does this mean? This means that it's player 1's turn to move, and player 1 can make any one of these moves, let's say A, B or C, and then the game position goes to these. Here for instance player 2 could be moving, here again player 1 could be moving, etc. This is the sort of thing. But there's no reason to only consider such a thing. You can also consider, for example, chance moves. For instance, you could have a move like this. Usually you represent them by squares, and then the game moves here. So it could be something like this. What does this mean? Here player 1's turn to move can either move here or move here. But when you get to a square node, it means nature intervenes. An oracle speaks and says you can go here or here. So typically this is also given with something like this. This means there is a chance move where with 1/3 probability you will be taken to this node next, 2/3 probability you will be taken to this node next. Right. But remember that player 1 has a control here to decide whether to go for a chance move or give a turn to the opponent. That's what it means. Now you can think of many such games, and it's extremely interesting too, even in combinatorial games that we were discussing, this kind of. So chance moves are also there. Now here suppose you have a utility like this. What does this mean? If play gets to this node with 1/3 probability, I'm going to get 15 and you're going to get 0. And if it gets here with 2/3 probability, both of us get to 6, 6. Right? Now in such a situation, how would you reason if you were given? But remember, this is a chance node. So what? Huh? Yeah, exactly. What's your expected payoff? What is player 1's expected payoff here? 1/3 of 15 plus 2/3 of 6. How much is that? Come on, 9. Right. And what about the other fellow? Poor fellow. Yeah. So what you can do is to replace such a node, right, by a node simply by, and then something happens, and here a leaf node with, since these were leaf nodes I am writing that, of course, otherwise it will, yeah, you can do that. Now this is how it is done. Of course a lot of economists question this also, because I mean, if it's 15, it's one thing. If it's $15 million and in the other one here, suppose for instance this was 0, right, would you actually take expected payoffs, or would you rather go for certainty? So these are all like funny situations, and you can think through a lot of examples to see whether it makes sense or not. I'm not going into that. I'm only saying that there is at least one mathematical way you can treat this, and people do this. That's all. I'm not into that. There are some philosophical issues involved about decision theory and so on. Right? But so all I meant was that I have so far not talked about chance moves, but you can bring in chance moves quite happily as long as you're working with not payoffs but expected payoffs. Win-lose, it doesn't make sense, right? In one, if I'm winning and the other one I'm losing, I can't average the two and say that I have a half chance of winning, let me go down. So it doesn't make sense. So the moment you move to outcomes, it doesn't matter and you can deal with all these. So this is one point. Second point is that, okay, another way that you can think of is, I'm not really interested in this flow of how the game proceeds, right? I'm interested in maximizing my utilities, right? I know that the other guy is planning to maximize his utilities. So we just try to see who will play what, right? Who will use which strategy, right? Now, what is a strategy for us? A strategy is a map from tree nodes to moves for each of the players, right? Now, given any finite tree, how many strategies can you have? Some finite number of strategies, right? So I might as well list them, sigma 1, sigma 2, sigma 3. So given a tree, I have so many possibilities, sigma 1 to sigma m. For the opponent, how many strategies can you have? So many possibilities, tau 1, tau 2, tau n. Now I know that every pair of strategies results in a play, right? And that play results in a payoff, right? The moment I say this is my strategy is sigma I and your strategy is tau j, I have some u1, u2. In fact, I should write it like this, right? This is it, right? So I can take this, and for every pair there is such a thing. Represent it as a matrix and look at the matrix entries. And this is all that we are interested in, right? How we arrive at the strategy, we need not worry about. We said anyway, right in the beginning, that I am not looking into how a player selects his or her strategy, right? So far, what is the assumption? For losing, winning, everything, what did we mean? We only meant existence of a winning strategy, right? How you come up with that winning strategy, how you compute it, how you actually play, whether you compute it beforehand and come to the game or compute it online, we didn't want to get into these details. And once you decide that you are not going to get into these things, you might as well say that your perfect player will know what to do with any of these strategies. So the only question is, if in such a thing, what does it mean? I am coming to the game having made up my mind that I am going to play sigma I. You are walking into the game having made up your mind that you are going to play tau j. If that is so, what will happen? You will play according to tau j, I will play according to sigma I, right? The only trouble is, when I am walking into the game, I have no idea which one you are going to pick, right? I have no idea where you are going to go, right? Similarly, when you walk into the game, you have no clue which one you are going. So what is the theory that we need at this point? A theory that predicts what rational players would do, right? So what I am doing is, I am walking into the game. So this is called games in strategic form. Note that we are doing precisely that kind of analysis, but we are doing it in a slightly different way now. What are we talking about? I am walking into the game and I want to pick one of these, right? Remember that this whole thing, the critical thing that you gloss over is online strategizing. You are not talking about online strategizing at all. If I am going to do offline strategizing, right, how will I do it? There are only so many possibilities of strategies for me. I have to pick one. How do I pick a particular strategy? I say, okay, these are all the possibilities. Against each one of them, I have to consider what my opponent might be doing, right? So what the theory says, that assuming that the other guy is rational, right? What does it mean to say that the other guy is rational?
He's only looking for his profit.
Well, yeah, maximize the utilities, right? So let's, yeah. So opponent is trying to maximize utilities, right? Then you can say that if there is between, so for instance in these two, in this playing this, right? If I am playing this, I don't expect that the other guy will play this. Being rational, you would look for the higher value, right? Now, you can question these things, but I am saying this is the idea, right? Symmetrically, what is extremely interesting is that the other guy is not only rational, the other person is also intelligent, which means that my opponent is also going to realize that I am maximizing, I am a rational player, right? Symmetrically, in column analysis, our friend will be going down columns and say, he is going to play this rather than that because it gets him better value, right? So symmetrically, both are going to apply rationality assumptions, and now the idea of the theory is to predict what these rational players will do. So what is the notion of a rational player? A rational player maximizes utilities, assumes that every other player is rational, and assumes that every other player assumes that everyone is rational, and so on. Okay, this is what is called, you are rational, you know I am rational, I know that you know that I am rational. This is extremely important, right? Supposing you are at a traffic signal, right? I am at a traffic signal, north, south, light is red. Actually, light is red is not a problem, right? What should I do? I should go across. But right then I see a car coming in the east-west direction, right? If this is green, that side is red. I don't have to see it. I know that it should be red. But now suppose I suspect that that's a joker who is going to, every red light he always goes through. Then what should I do? Being a rational guy, I cannot argue that it's red, therefore he will stop. If I suspect that he is a joker, I have to allow for the possibility that he will come across, right? In which case I will not move even if my light is green. Symmetrically, what about the other guy? He is coming towards this, right? If it is green, right, if it turns green, he has to go. But again, he can assume if he is worried that I am a joker, he will not move. So in fact, unless you have a common knowledge of the convention, right, that red means stop, green means go, that everyone acts according to that, and everyone assumes that everyone acts according to that, and so on, that infinite iteration. Unless that happens, your traffic signal will be deadlocked. Everyone will be waiting and not willing to take a chance. So for it to move, you need something like that. So this is what Clark and Marshall call the common ground. Common ground is something that is there in most interactive behavior. Some common ground against which we take actions.
The concept of offline which you said, isn't it similar, equivalent to both players, each turn picking it simultaneously? Each turn, it's equal.
Yeah. The moment you have decided that, you are going to pick one of these. So what you are saying is independently, autonomously both pick strategies. It's not just simultaneously, but without knowledge of what the other guy is doing, right?
Yes, but the turn, suppose I have picked up the I turns. The I plus one term, I know what are the three. But still, I plus one turn, both of us pick simultaneously.
That is not necessary. I am saying this picture, in this picture it's strictly turn based, right? There is no simultaneous moves. I am saying from this now, if I have pulled out a strategy, that strategy is going to tell me what to do here, what to do there, what to do there, etc. Even if not reachable once, it will tell me, right? That strategy that I am picking here, right? Picking those functional strategies is something simultaneous. That's offline. That's the point. Okay. So I am not talking about having concurrent moves here. No. I am talking about.
This is too strong a constraint.
Oh, we can discuss that later. I mean, these game models can be discussed endlessly, and I would love to, but it's just that I want to take some standard game model and proceed. That's all. Yeah, I am not a great fan of this way of.
Isn't it equivalent?
No, it's not equivalent, is what I'm. Right. So this is the important point. But having concurrent here is a different thing altogether. The notion of strategizing is completely different. You see, your notion of strategy, functional notion of strategy, completely changes. So it's with respect to the turn-based notion of strategy that I'm talking about a matrix form, right? In which case I'm talking about offline picking these strategies, listing them, and now I have to analyze, right? Okay, this is what we want to do. So how do you analyze such games? Let me just mention some examples. Is it correct? It is. Okay. So let me mention some example games and then we can start off. So now, so the deal is that so now we can forget about how these strategies are constructed. For player 1 there is a set of strategies, for player 2 there is a set of strategies. simply call them 1, 2, 3, etc. Suppose player 1 has 5 strategies, player 2 has 8 strategies, there is a 5 by 8 matrix with pairs as entries, pairs of real numbers as entries, and you want to see how players would play, right? Now, there is an obvious notion of what is called a dominated strategy. And the thing begin with. Let me mention that and then we'll continue tomorrow. So there is a classic game, there is a kind of a law which says that you can't lecture on game theory without mentioning this game, so I have to do it, even if I do it at the end, and this is called the prisoner's dilemma. The story goes that there are 2 prisoners, right, who are caught near the scene of a terrible crime. Some US, this all comes from the US. Right? So, murder, gore, blood, and so on, right, in some supermarket apparently. So these 2 guys are caught near, in the adjoining block and with guns on hand. But there is no direct physical evidence linking them to the actual crime itself. But possessing guns is illegal in that particular part of the story, in that part of the world where the story happens. So there are these 2 guys. They are caught in 2 rooms and interrogated separately with hopefully torture elements and so on, appropriate things. And they are asked, confess. So now each prisoner has a choice. There are only 2 choices. So 2 strategies: confess, deny. Confess, deny. Now, if both confess to the crime, you go to 20 years jail, 20 years. So I can write this as a payoff minus 20, minus 20. If both deny, there is no way of proving that they committed the crime, but there is a bad enough scene of possessing a gun for which you go to jail for 1 year. So both get minus 1, minus 1. But there is one option. This guy here is saying that if you confess and you turn a prover, testify in court against the other fellow, then, okay, so let's say minus 10 in this case, 10 years. Both confess, so they get slightly less. Right. So if you confess and the other guy denies, so actually in this fashion. So if I confess and he confesses, we both get minus 10. If I confess, I get 0 and the other fellow gets 20. If I deny this, if we both deny, we both get. This is the notation I use. This makes it clear who gets what. Yeah. This is the row player, this is the column player. Payoffs. Is the story clear? Now how should they act? I think they're usually called John and Jack or something like that. So how does John reason? John reasons that, yeah, I have no idea what Jack is doing at this point, right? Maybe Jack is confessing. If he confesses, right, what should I do? If he is confessing, I should also confess. Suppose he is denying, right? He is speaking denial, right? If I deny, I will get minus 1, but if I keep my mouth shut, if I confess, in this case, I get 0. So either of the options that he is using, confess is better for me, right? Then I argue that symmetrically Jack must be doing exactly this reasoning, and he would also come up with confess as the option, and therefore we both confess. So the strategy confess strictly dominates any other strategy. In this case, therefore, that's what they would pick. But this itself is, that's why this prisoner's dilemma is something that books have been written on, cause of much angst in game theory, because there is another option, right? Surely both should keep their mouth shut and deny, and both can walk away with just 1 year in jail, right? Why would they want to go for 10 years in jail? But this is the prediction, right? Now, this is the kind of analysis that we are talking about. In general, so much of this style of equilibrium theory is that you are given a matrix, right? You are given a matrix with some payoffs that are given to you, and this payoffs could be actual payoffs or expected payoffs averaged over something, right? So what basically you interpret the numbers, the real numbers in the matrix as constituting expected payoffs for players. Now you are asking how players would play, each one attempting to maximize utilities and assuming that the other players do likewise. Then you predict what the players would do. So this is, and this is called equilibrium theory, because what you want to come up with is one where if you predict that these two guys will play, it should be it should be invariant under very small perturbations, right? What does that mean? We'll see all this, right? There should be no way of deviating from what you are saying. That's when you will call it an equilibrium. Okay, so we'll take this up tomorrow and see what they are